So, the last time we were doing probabilistic methods. So, we will be doing many examples. First, we showed the example of Ramsey number, which is also you are coloring the graph, the edges red or blue, and then you are interested in monochromatic complete subgraphs. This you can also see as the presence of a clique or an independent set. Okay, you can think of complete graph on red as clique and blue as absent edges, which means that it's an independent set. Second example we did was about the existence and also finding a large cut in a graph. Okay, so a subset so that the edges going out are maximized. Then we did sum free subset, right. So, given a set of numbers, finding a subset which is devoid of any sum. So, A plus B should not be equal to C, A, B, C in the same subset. And then we started discrepancy. So, here you are given n unit vectors, you do not have any information about VIs except that they are in ambient space n, real coordinates. Now, you want to take a signed sum, this sigma bi vi, so that the norm is minimized. And we will show how to find a signed sum where the norm is smaller than square root n. Okay, so, note that the signed sum will have norm, you expect it to have norm around n because VIs are unit vectors, but this is far better than that. This is giving you square root n. The idea here is, as should be clear by now, that we will pick BIs randomly. So, you pick BI to be -1 + 1 by a coin toss. Randomly, in fact, you do it in an IID fashion, right, which is independent and identically distributed. Okay, so, these are, you flip basically n distinct coins independently. So, what is the expected value of sigma bi vi? Right, what do you expect this to be? So, let us do that calculation. So, define random variable x as the square root of this. Okay, let me first do this. Define it to be the norm of bi vi. Okay, so this is what we are interested in. So, what is the expectation of this? Remember that this is a real valued, positive real valued in fact. So, this is a non-negative real valued random variable. And now we will calculate its expectation. So, x square is essentially it is sigma bi vi transpose multiplied by itself, right. So, this is the inner product. In other words, advantage is you can expand it out. So this is equal to sigma bi bj times vi transpose vj. Okay, and let us instead calculate the expectation of this, expectation of x square. So that is by linearity of expectation you get pi bj and vi transpose vj is fixed value. So that goes out. Remember bi bj is what you are picking randomly in an IID fashion, right? So if I and j are different, then because of independence this will factor. Otherwise you are looking at expectation of a square. So let's do that. So expectation of pi square times this plus expectation of bi bj times vi transpose times vj. So this is equal to expectation of bi square. So bi square is 1, right? So that is 1, and you are looking at vi transpose vi, which is actually norm of vi, which is also 1. So you get n plus what is expectation of bi? Expectation of bi is 0, right? Minus 1 plus 1. So you get n. So here we used independence. And notice that actually 2 y's independence would have been enough for this calculation. And the other thing we are using is that expectation of bi is 0. So that gives you expectation of x square to be n, which means that there indeed exists this choice b1 to bn such that x square is less than equal to n. Since the expectation of the random variable x square is n, so there has to be a choice such that its value is less than equal to n, in respectively greater than equal to n, right? Nothing special about that. So which means notice that x is by definition it's non-negative, right? So this is if and only if there exists b bar such that x is less than equal to square root n, respectively greater than equal to square root n. Okay, so we just wanted to show that there is a choice of bi's such that this x is at most square root n, and that is true. That is what expectation has shown. Okay, so this is a useful calculation. It actually appears in many places, this expectation of square computation and use of 2 y's independence. Okay, so you have seen 4 examples of probabilistic methods. Now we will work out the 5th one, which will be slightly more complicated. So this is about extremal set families. So what is that? So define a family of set pairs let's say H pairs it is called KL system if AIs are of size K, BIs of size L. Let me call this BJ. And if you look at the intersection of AI with the same with the other set BI in the same pair, they are disjoint. For all I, and if you look at the intersection with something else, then it's not. Okay, for all I different from J. So again, A's are of the same size, B's of the same size, which is respectively K and L. In the same pair, these two sets are disjoint, but across pairs, they overlap. Right, that is called a KL system of sets. So let's see an example first. So let the universe be first K plus L numbers. Then if you look at the family where first is a subset of U and the other is its complement. And take A to be a subset of U of size K, right? Thus, A complement has size L, right? Because universe has K plus L elements. So, A takes K and A complement takes L. So, you can see that in a single pair, A complement are disjoint, while if you go across pairs, then they will overlap. So, you can see as an exercise that this is a KL system. So, you can check this. And what is the size of this KL system? Each, so this size is K plus L, choose K. Right, that's the number of subset A that you can have of the universe. So, the question to ask is, there a larger F? For a fixed KL? So, can you, given K and L, can you find a K comma L system where the number of set pairs is more than K plus L, choose K, right? That is the question. Now, a priori there is simply no intuition whether the answer is yes or no. You can try at this point either direction. What we will show, that is theorem 5. Right, we have done till theorem 4, yeah. So, theorem 5 is due to Bolo-Bash. Saying that F is KL system. Then if F is KL system, then previous example is the best. That is, F is smaller than K plus L, choose L. Okay, so any KL system of set pairs cannot have size more than what you just saw. k plus L choose k is the best. This upper bound seems stunning, but the proof is really simple by probabilistic method. Okay, so what you have to do is kind of take inspiration from this example. So in this example, the universe was ordered, right? You had this 1 to k plus L. So kind of map every example to this example via ordering. So the idea is define the universe to be AI union BI for all I 1 to H and consider a random order pi on U. Okay, so randomly map this universe to kind of what you saw before, and what is the contradiction or what is the argument now? How does it help? So for that, consider the event EI, event that elements of AI precede BI. In this order pi, what is the chance that in a set pair, in the ith set pair, AI has elements all smaller than all the elements of BI? Okay, so there is a marker, AI is completely on the left and BI is completely on the right. With respect to order pi. Okay, so this is event EI. What's the probability of this happening? Well, so assuming that you have fixed pi or you have chosen pi, AI is essentially k elements that you want to pick. You will pick these k elements and BI are L elements. You want to pick k preceding. Sorry, you have to first remember that AI, BI are also given, right? AI, BI is fixed. So let me write that. So for the given AI, BI, pi will keep AI before BI with probability so basically you just focus on these k plus L elements, and what is the chance that pi will pick the first k before the remaining L, right? So that is just the probability of choosing a k subset out of k plus L. So it's 1 over k plus L choose L. K plus L choose k also you can say. So this is the number of ways the first k can be chosen, and out of this AI is the only correct one. So it's actually 1 out of all these possibilities, right? That's the number of first k, number of ways pi can pick first k elements. And out of this only 1 is correct, which is AI, right? So this is 1 over k plus L choose k, which is equal to 1 over k plus L choose L. So that's the probability of EI event. And what can you say about these events? So E1 and E2, or in general EI and EJ for different IJ, right? Are they dependent? Are they independent? Are they disjoint? What can you say about that? So I claim that EI and EJ are disjoint events. So yeah, this may not be clear immediately, but once you think about the definition of disjointness, you will understand. So suppose they overlap. There is some common case. So what is the common case? Suppose there is a order pi. So there is an order pi under which, or with respect to which, AI is all behind BI and AJ is also behind BJ. Right. So first is event EI, the second is event EJ, and there is a common order pi which is achieving both the things. Now, is this possible? Well, let us assume without loss of generality that max of AI, so compare max of AI with max of AJ, right. So suppose max of AI is less than max of AJ. But max of AJ you know is less than every element in BJ, right. So AI goes completely behind BJ. With respect to pi, which means what? In particular, it means that AI and BJ cannot intersect. Right, which is a contradiction, which means that EI, EJ are disjoint. Okay, they don't have a common pi. So in some sense, this E1 to EH, right, they are giving you a partition. So EI is saying is the event that yeah, EI precedes BI, and so if A1 precedes B1, then A2 cannot precede B2. Okay, this is what you have learnt. So what you can deduce from this is that one is, if you look at the union of EIs, union of these events, then that is actually sum of the events. Okay, so you are actually getting a partition of union of EI, and that of course is less than or equal to 1, right. Probabilities are always less than or equal to 1. So we have that the sum is less than or equal to 1, but what is this sum? What is probability of EI? So that we have calculated, right. That was 1 over k plus L choose k. So you have calculated H over k plus L choose L, which implies that H is less than or equal to the binomial number or the binomial coefficient. Okay, so we have shown that by this ordering, by picking a random order, you actually get an upper bound on how many AIBIs are there, right? So this is a very short proof, relatively simple, but it's proving this statement which had nothing to do with probability or ordering, right? Completely devoid of any character except this set family properties. Okay. So with this, let me move to the final example of probabilistic method. So sixth example is super concentrators. So these are again kind of extremal graphs. These are extremal situations. It's a graph which is highly connected, and we'll make it precise. And then using probabilistic method, we'll actually give a way to construct them. So let us first see the definition. So super concentrator is a directed acyclic graph G. So basically, it's the edges are directed and there is no cycle. Okay, it's a directed acyclic graph with two designated subset of vertices. One we will call input, the other we will call output. So with n special input nodes I and n output nodes O, such that, so here comes the heavy connectivity between input nodes and output nodes. So no matter what subset you pick of I, respectively that of O, you will have disjoint paths between them or across them. So for all k, for all s I to k, and for all t, sorry, S is a k subset of I choose k, and T is a k subset of output nodes. So O choose k. For all ST, S connects to T with k disjoint paths. Okay, so the vertices S, they connect to vertices T. So k on the left, k on the right, you can think, but via k disjoint paths. So what is the importance of k disjoint paths, right? The thing is that if you think of like a physically wired telecommunications network, then for people in the set S to talk to people in the set T, you want really disjoint connections. Okay, if the connections overlap, then the calls will overlap. So that really is the motivation of this definition. So example, this allows a robust telecommunications network. So any k people in I can talk to any k in O simultaneously. Okay, this is the importance. So any k people in input nodes can talk to any k in output nodes. So you can think of them as the communities, and simultaneous connection is there, right? Simultaneously they can talk. So these are the wires. These wires don't overlap. Now, do these things even exist? So actually, existence is not a problem because a complete graph, and then these connections will be there. Okay, so these things trivially exist. So let us note that down. So a super concentrator exists with the vertices 2n and edges n square. Right, so you can look at the bipartite graph, n vertices on left, n vertices on the right, all the edges are there. So then trivially you have any subset on the left can talk to any subset on the right via this matching. Right, so that is actually trivial. N square is there. So what is the question then? The question is, could you reduce the number of edges? Could you really get a linear sized graph? So could we optimize, let me say. So that vertices and edges both are linear in n. Okay, you want the vertices and the edges to be roughly of the same size, and hence linear construction. Okay, and that existence is now not clear.